Okay, so good day. So in this video, we are trying to derive the basic equations or formulas that we need to use for an isometric process, specifically in thermodynamics. Okay, so where will we start? So let's start first. What is an isometric process? Okay, so take note when you are studying or when you are performing problems or um, equations, or you're generating equations for processes of ideal gases, you need to be familiarized first with two of the basic charts or two of the basic graphs that you need to be familiarized with. So what are those? So we have number one, PV diagram, or the pressure volume diagram, and the TS diagram, that is the temperature and entropy diagram. Okay, so in an isometric process, the first assumption that we need to consider in an isometric process is that the volume is always or is considered to be constant. So there are no changes in the volume of your substance. So an example of this one, or the application of this one, are pressure cookers, tanks, even rice cookers. Okay, so those are the basic examples of isometric processes wherein the volume, regardless of the pressure and the temperature that is occurring inside of that vessel, the volume will not change at all. Okay? Take note that the constant volume process may be reversible or irreversible. Okay? So in the PV diagram, if you observe, when we are dealing with an isometric process, it is always represented by a straight vertical line. Okay? Laging straight vertical line, because as you can see, from point 1 to point 2, the volume is constant. It is consistent overall. So the pressure, so we know that the pressure, what will happen to the pressure during isometric process? So afterwards, after undergoing a certain process, the pressure will eventually rise. Okay? Same goes with the temperature. In T1, from T1 to T2, the temperature elevates. Okay? So, what is the first step when we are dealing with processes of ideal gas? Of course, write your assumption. Okay? So in this case, our assumption is that the volume is said to be constant. Next, let's proceed first with combined gas law. So what is the combined gas law? So combined gas law is the ratio between P1 V1 over T1 is equal to P2 V2 T2. So that is your combined gas law. Okay? So as we've said in our assumption, volume is said to be constant. So therefore V1 cancel out and V2 as well, because they are constant with each other. Therefore they will relatively cancel each other out, leaving us with P1 T1 is equal to P2 T2. Okay? By performing separation of variables, all the pressure and temperature are together on both sides of the equation. Okay? So let's say T2, I want to place temperature on the left side. I will have T2 over T1, and on the right side I will have pressure, which is P2 over P1. So this is your equation number 1. Okay? Next, take note that in some problems, they will not tell you that the process is constant volume. So what are the keywords when we are dealing with constant volume? So number 1, you are dealing with a tank, you are dealing with a drum, you are dealing with a rigid vessel, or sometimes it is a frictionless vessel. Okay? Sometimes lang yan, frictionless. Okay? So, those are the keywords. So, once you are dealing with those problems, let's say in the first question, a tank is blah blah blah. So, you can assume immediately that this is a constant volume process. Okay? Next. So, let's proceed with the change in internal energy. So take note that the change in internal energy is the equation for it is always absolute. What do I mean when I talk about it is absolute? Regardless of the process, it is always consistent. So, hindi siya nag-iiba. So, it is given by m CV dt. Okay? So, this is your equation number 2. Next, the change in enthalpy. Just like with the change in internal energy, the change in enthalpy also is absolute. So, hindi rin nagbabago yung equation niya, which is given by m Cp dt. Okay? So, Cv and Cp corresponds to your specific heats. Okay? Cv correspond to your specific heat during constant volume, whereas Cp corresponds to your specific heat during constant pressure. Okay? Next, leading us to the equation of, so letter D, heat. So the general equation for heat is mc dt. Okay? Take note that the heat is always dependent upon the process wherein the gas is undergoing. Okay? So in this case, it undergoes a constant volume process. So therefore, we can say that Q is equal to m Cv dt. Okay? But as you can notice, equation number 4 and equation number 2 are the same, leading us with the conclusion, therefore, during isometric process, delta U is equal to Q. Okay? So don't forget this one, ha? So delta U is equal to Q. Okay? Next, letter D. So what if we are asked to solve for the non-flow work? So we know that the equation for the non-flow work is the integral of P dV from point 1 to point 2. Okay? Next, our assumption earlier is that the volume is constant. Okay? So since that the volume is constant, let's try to substitute it here in this term. We will have the integral from point 1 to 2 of P dC, or this V, we substitute it by C. Okay? So this term, it simply implies that we are taking the derivative of a constant multiplied by function P. Okay? So in differential calculus, if we are asked to locate for the derivative of a constant, let's say 5, we know that the derivative of 5 is equal to 0. Anything that is constant, the derivative of it is 0. Because in derivatives, we are measuring the rate of change. If it is constant, therefore there is nothing changing in the system or in the substance. Okay? So therefore, we can conclude that this term is equal to 0. Okay? So regardless of how huge the magnitude of function P is, if anything that is multiplied to 0 is equal to, very good, 0. So therefore, the non-flow work is equal to 0 during an isometric process. Okay? Next, so this is equation number 5. Next, so what if we are asked to locate for the steady flow work? So that is given by negative V dP. Okay? So same rule applies as earlier. So we know that the volume is constant. Okay? So we can replace V here by C dP from 1 to 2. Okay? Next, as a rule of integration, what do we do with constant inside of an integral sign? Very good. So we eliminate it inside the integral sign, wherein we place it outside of it. So that is negative C integral of dP from point 1 to point 2. Okay? So we have a derivative multiplied by antiderivative. It will cancel out. We'll have negative C, that is from P2 minus P sub 1. Okay? However, we've said that V is equal to C. So, let's return it from its original equation. Susulat natin dito. So, the non-flow work, or the steady flow work, I mean, is negative V times P sub 2 minus P sub 1. P sub 1. Okay? So, this is your equation number 6. Okay? Next. Letter E. So, letter E, this is the change in entropy, which is given by the integral of dq over t from point 1 to point 2. Okay? So, as we've mentioned earlier, here, q is equal to delta u, which is given by this equation, mcv dt. So, let's try to substitute dq here in the equation of entropy. So, we will have from point 1 to point 2, dq is said to be equal to delta u, which is given by mcv dt over t. Okay? So, in processes of ideal gas, we are always assuming that the mass is conserved and also there are no losses within the mass. So, mass is being a constant, so therefore we need to place it outside of the integral sign, and also Cv is a constant because that is your specific heat during constant volume. So, alongside with m, lalabas din natin siya sa integral sign. So, leaving us with the change in entropy is equal to mcv integral of from point 1 to point 2 of dt over t. Okay? So, if we evaluate this integral, if we have the integral of du over u, so you will have ln of u plus c. So, quick review of your integral. So, we can rewrite the change in entropy as mcv ln of T2 over T1. Okay? So, this is your equation number 7. So, I hope you understand the derivation. So, this is the part 1 of our video presentation. On the next video, we will try to apply all of these parameters or all of this equation in a problem solving. So, I hope to see you in the next video. So, thank you for joining and see you on the next video.